has been a major issue. And naturally, many researchers, scientists, and pharma representatives have been working on this issue. How could we deliver medication or drugs locally, just into the target and nowhere else? Maximize the effective target, deliver the drug at high concentrations while minimizing the concentration of the drug elsewhere so that it doesn't interact with the heart and other organs that you would like it not to interact with. It's a big, massive goal here. A lot of people have been working on this. And one of the most attractive approaches to deal with local release in the human body has been to use focused ultrasonic waves. So if you want to release a drug locally, you need some kind of carrier, right? And you need some form of energy. And one of the marvelous properties of ultrasound is you can actually focus it selectively into the target, have high intensity there and low intensity elsewhere. So that achieves the selectivity while impacting nanoparticle carriers. So at the focus of the ultrasound, the nanoparticle carriers are activated and release the drug. And the ultrasound has been attractive because it can be highly focal and it still propagates through the body. Now, that seems like a sound solution. And in fact, many people have been working on this. They have developed nanoparticle carriers that vibrate in response to ultrasound. Think of it as bubble vibrating when you send sound waves into it. But there has been issues because the nanoparticles have been either effective or safe, but not both. So there has been a massive undertaking to try to solve that issue. And Matt, not being afraid to take that challenge, joined my lab 5 years ago with the vision that we'll crack it. We have cracked it, we believe, as Matt will show you. Matt has developed nanoparticle carrier that can be safely administered into non-human primates while being sensitive to ultrasound and release the drug. So it's both effective and safe. And I should really stress that this thus far has been confined to rodents because it has been either effective or safe, but not both. Matt, to my knowledge, is the first person who has brought it to non-human primates as a functioning, effective, and safe vehicle. And that is massive, in my view. So Matt has really undertaken a heroic deed here. He has designed the nanoparticles, previous formulations, redesigned them such that they are sensitive to ultrasound, while for the first time being also safe, that you can inject it into a monkey, primate. For the first time, nobody has done this before. He has subsequently trained the monkeys on a choice task. That's not easy to do. Head fixed away monkey, playing a little game, making choices. He has made sure that he can inject the nanoparticles through a vascular access port that's implanted into the monkey saphenous vein here. Also not easy to do. So the monkeys now carry vascular access ports with Caroline's help. And while the animals are performing the tasks, he injects the drug, mounts an ultrasonic array on the head of the animal, focuses the ultrasound into specific deep brain regions, and selectively releases the drug in specific brain targets, showing that he can modulate choice behavior that way. That's a really, really difficult project. And so I wanted to really take you through all the steps that Matt had to go through this. It's a really heroic deed, and he has done it. He has published on that. Matt has published 7 articles during his PhD work, 3 as a first author. But not only that, he has also mentored students, and many of them actually. That includes graduate students, undergraduate students, and a high school student. Besides the academic matters, he has also been involved in student organizations very actively. And so he has really represented all the tasks and duties of a future successful doctoral candidate. Enough from me, a very unique candidate. We are very excited to hear his talk. Matt, it's yours.
Wow, thank you. Thanks so much. That was a really nice intro. Uh, and thanks everyone for coming. I'm super excited to have you all here and show you what we've been working on the last few years and add a few pictures to what Jan's described. Yeah, so yeah, this work is called Targeted Pharmacological Neuromodulation, as Jan has suggested, because we're delivering drugs to specific areas in the brain. Now, the overall goal of this work has been to resolve this problem, which is that localized conditions are often treated with global methods. So in the case of mental and neurological disorders, these things often arise from individual areas within the brain. And yet we treat them with drugs that affect not only the entire brain, but also the entire body. So you're having limited effects at the target, as well as a bunch of side effects from off of the target. Another application is cancer, where, especially in the case of brain cancers, you have a tumor that arises in the brain, and then you try to treat it with drugs often, and those drugs go everywhere, and often not even into the tumor in the case of brain tumors. So you can probably think of a whole bunch more examples of areas where this would be useful, but I want to focus here first on mental illness. So the problem, as I mentioned before, is that these things are treated with antidepressants frequently. And as you can see in this plot, this is comparing a placebo treatment on the left with an antidepressant treatment on the right. And these green people had an improvement in symptoms during this study. So as you can see, for about 20% of individuals, there's an improvement with antidepressants over placebo. That's awesome for that 20%, but it still leaves a lot of people untreated. So we have limited efficacy. And to add on to that, most patients experience side effects with these medications, if they're even able to do that in the end. So our goal is to localize the effects of these drugs to specific targets within the brain non-invasively, so without poking anything in there. So we want drugs just where we want them, like this guy with the purple dot, but not elsewhere. So as Jan mentioned, this requires a drug carrier that we inject systemically, and then an externally applied energy source. So let's talk about that energy a little bit. Now, focused ultrasound, as Jan mentioned, is really cool. You can focus it to individual targets deep within the brain or other parts of the body, and it's non-invasive. So this is the only way that we're aware of that you can target small areas non-invasively, at depth at least. And so it's really cool because it pushes and pulls on tissue, and you can have a variety of things happen at the target. And the way that this works is that you can have all of these elements that are placed outside of the brain, outside of the head, and focus them into individual areas. So we do that by the concept of interference. So this is just demonstrating how we add together sound waves at the target. So as you can see, if these two sound waves on the left arrive at the target at the same time, they become a bigger sound wave. Whereas if they don't arrive at the same time, they can cancel each other out. So you have no effects in that case, but a much larger effect on the left. So if you imagine we expand this out to hundreds of elements, we can then steer around and target individual areas within the brain non-invasively. So this is awesome, and we can achieve specific effects only at the target by loading these drug carriers with whatever drugs we need, and then we can have just the effects that we want at the target. So let's get a little bit into those drug carriers now. A lot of previous approaches started with some temperature-sensitive liposomes. So these are very small particles, which are injected systemically, and they float throughout the bloodstream. And then when they're heated up, their membrane becomes a little bit more permeable, and then the drugs that are in them can come out, at least in theory. The issue with these is that by heating the tissue, you have a risk of causing damage. So there's a very small window where you're actually getting effective release of drug from them without damaging tissue, which is a risk, especially in the brain, where you don't want to burn tissue. And in addition, these were really unstable. So they're broken down within the bloodstream within just a few minutes. So it was difficult to even get drug to the target in a localized way. So some other researchers have focused on using microbubbles, which are much larger, and they have a gas-filled core. So this leverages the mechanical nature of ultrasound that I talked about before. So you're just pushing and pulling on these bubbles and they oscillate. And by doing so, you can actually disrupt vasculature, which can be useful for delivering drugs, but it also adds increased risks. So if you're disrupting vasculature, if you're disrupting the blood-brain barrier, for instance, in the brain, this can lead to inflammation. And so if we don't need to do that, it would be preferable not to. Another issue with these microbubbles is, again, they don't last very long in the bloodstream because your body can easily recognize them and clear them out. So it's, again, difficult to get drug to the target using these. So a really promising approach has been to use these much smaller nanodroplets. So they use a similar compound as the microbubbles, but instead of a gas, it's a liquid, and they're much smaller. So the concept here is that we use a copolymer shell. So this shell will isolate the drug that's contained within it from the environment as it flows throughout the bloodstream. And then when the particles are at the target, we can simulate them with ultrasound, and they have a perfluorocarbon core, which sort of gives them their ultrasound responsiveness. So this is just a little cartoon of how that works. As you can see, when they're hit with ultrasound, they expand and the drug comes out. So we can actually visualize this if we do ultrasound imaging. So this is a great video the student in our lab captured. This is a standard ultrasound image like you would get if you're pregnant and you were looking for your fetuses. You can actually see the bubbles, or the particles rather, as they're hit with the ultrasound at the focus, which is represented by that dotted area. So this seems really promising, but these approaches have been limited in the past by several key barriers that have kept them out of clinical use. And the main objective of my research has been to eliminate those barriers so that we can eventually use this in humans. So the first major barrier has been the use of these volatile perfluorocarbon cores. So up until now, most researchers have focused on using really low boiling point cores in their particles. So as you can imagine, since the boiling point is so low, they're really sensitive. And if they're heated up just a little bit, in fact, their boiling point is below human body temperature. So you have a huge risk of them bubbling up away from the target, which can give you a risk of embolism or clogging up blood vessels, as well as just potential off-target effects. So what we've done is we use perfluorooctyl bromide, which is a really high boiling point core, and it's been very thoroughly studied and suspected to be safe. So we wanted to use that in our particles. Once we addressed that issue, we moved on. Most of these studies, in fact, all of them, have been done in rodents. And as anyone out here probably knows, rodents are very different than humans. They're much smaller. Their bodies work differently. And so you don't always know, like, if you develop a treatment for a mouse or a rat, is it going to work in a human? So we wanted to advance the field a little bit and do this in non-human primates, in particular macaques. And this is why I wear my monkey socks today. So we got to represent the monkeys. And finally, the last barrier is one that anyone who works in ultrasound is familiar with, which is the human skull. This is a really difficult problem for anyone who wants to get ultrasound into the brain. And in our lab, we've developed a way to get ultrasound through the skull and obtain effective drug release there. So to skip a little bit to the punchline, I'm going to show my favorite figure, which comes up a bunch in this presentation. This is basically showing localized anesthesia of deep brain regions in our primates. So don't worry too much about what's going on here. I'll explain it all in detail. But effectively, this gap where we have propofol nanoparticles compared to not propofol nanoparticles, there's a substantial bias in a monkey's behavior. So we're able to control a monkey's visual processing by delivering propofol to individual deep brain regions. So basically, the entirety of my work in the last 5 years has been to get this gap between these two lines. So I really like this figure. And what's also exciting is that this is representing 80 sessions across 2 monkeys. So this is a ton of sessions, and it gives us pretty good confidence that it's fairly safe because we've seen no side effects as a result of giving them these nanoparticles a whole bunch of times. So aside from removing barriers to translation, we've had all this scientific output. As Jan mentioned, these 3 first author papers and several other publications that have come out of it. But now let's get into what actually went into getting this done. And first, we had to develop and characterize our stable ultrasound responsive drug carriers. And in particular, in this study, we were looking at the perfluorocarbon core. Now to give you a little bit more background, in past studies, the boiling point of the core has seemed really important to how much drug you actually get out of the particles. So here, the black and the gray bars represent 2 different boiling points of perfluorocarbon. So the black is a much lower boiling point, so it means it is more volatile than the other one. And as you can see, it has a much lower ultrasound pressure to activate it and to obtain drug release. So a bunch of other people have seen this too. So many researchers have gone on to then focus on these really low boiling point cores, thinking that this is the only way that we can actually effectively get drug at the target. And the problem that you have with these is that they're very unstable. So let me show you a little bit of data to back that up. So we made some nanodroplets in our lab out of perfluoropentane, which is even a much higher boiling point than those that we just mentioned. And we just put them in a test tube for 24 hours and measured their sizes at various time points along there. And what we found is that they dramatically increase in size. So they're basically either coming together or forming bubbles. They're quite unstable. And if you have a doubling in diameter of the particles, so this is a problem for us. What we did is we used perfluorooctyl bromide, PFOB, which has a much higher boiling point, and as you can see, is completely stable over 24 hours in vitro. So this is promising, and in fact, these have been studied PFOB has been studied at very high concentrations, at up to 2 grams per kilogram. When you compare with ours, we're at 0.14 grams per kilogram. So it's a minuscule amount of PFOB compared to what people have studied in the past. And they were actually studying it as a blood substitute. So they carry oxygen really well. So you can inject them in large quantities, either in the blood or in lungs, and you're able to transport oxygen that way. What's cool is this study way back in 1985 submerged a mouse in a perfluorocarbon for several hours, and then they pull the mouse out and it's still fine, which is crazy. I honestly, that's kind of unbelievable, but I guess it happened. And so, yeah, they seem generally quite safe. But the question is, does PFOB actually let you release drug? Because it's such a high boiling point. You're never going to get it to vaporize in the blood. So that's kind of the barrier that we wanted to address. So to do that, we tested 2 different ultrasound frequencies, as well as 3 different perfluorocarbon cores, so we could see if there was an effect of that boiling point and the frequency on the amount of drug that's released from the particles. Now we use PFP as a baseline for this because it's been studied in the past in vitro or in vivo, so in rodents. They were able to get effective drug release from it. So we sort of use that as like the gold standard for this in vitro test. The way that we do this is we have a little test tube that has a nanodroplet solution in it, and they're loaded with a drug, which is primarily propofol in the case of these tests. And we're able to measure the concentration from those nanodroplets. And then we apply our ultrasound from a source that's located below it. The drug is released from the particles, and then we can measure the drug concentration in a hexane, which is sitting on top of the nanoparticle solution. So hexane is just a really hydrophobic material that extracts the drug. So we're using hydrophobic drugs. So it extracts the drug nicely, and then we can see how much drug is released as a percentage. So before I show results, I have one more piece of background to give you, and that's about the ultrasound frequency. So if you're not familiar with ultrasound frequencies, there's a range that you can use. At lower frequencies, you tend to have a larger focus. You get more mechanical effects at the target, and it's easier to get it to penetrate at depth. So it goes through tissue more easily. On the other hand, high frequency ultrasound you can get a smaller focus with it. So it's kind of useful for rodent studies because you need to focus it in a teeny tiny brain. But then you don't know if it even is going to translate to a human because it's such a high frequency. Anyway, you're more likely to get thermal effects. So most studies in the past have used these high frequencies of ultrasound, which kind of alluding to that you also use low boiling point cores. So perhaps a thermal effect is happening. And also you can't get them to penetrate that depth as well. All right, so this is our results. This is aggregated drug release from the 3 different cores using high frequency ultrasound. And as you can see, this aligns pretty well with what other researchers have found, which is that the core is really important for how much drug is released. So the low boiling point cores work very well, whereas high boiling point cores look like they don't work at all. So this seems problematic until you add in low frequency ultrasound, where the core no longer matters. So we can use our really stable particles, and they're affected in pretty much the same way as the lower boiling point cores, while being much more stable, as I showed before. So this might seem really obvious to you. It felt like it should be obvious, but it was incredibly difficult to actually make these things and get to this point. A whole bunch of rounds of testing them, even using like protocols that were already published. I was making them in my garage during the pandemic, and it's just really hard. So that's a problem that we wanted to resolve for the field. So we wanted to create a recipe that would let people use whatever drug they want and configure these things however they want in their labs and replicate our results and hopefully do more cool, interesting things. So what we did is we practiced encapsulating several different drugs. And this is some work that Alex, an undergrad student in the lab, helped out with. Basically, we encapsulated propofol, ketamine, and mycophenolate motafil, which, aside from being hard to say, is a drug that is an immunosuppressant. So it's used for transplants where you want to suppress the immune system so you don't reject the transplant. The idea with this one, this is completely hypothetical, but the idea would be that you could maybe suppress the immune system just in the transplanted organ, but not the whole body. So anyway, these drug carriers generally can encapsulate and release a variety of drugs, is what we found. So we also wanted to make our manufacturing process more repeatable. So there's all these steps which are generally similar at different groups in the field. And you can actually do all of them slightly differently. And if you do a tiny thing different at each step, then you wind up with a completely different result. So we put Arav, our amazing high school student, to work on figuring out which parameters are important. And you don't need to worry too much about the actual contents of this, but effectively what we've done here is we provide a way to get the nanoparticles that you want by changing individual parameters in the manufacturing process. So maybe if you want more drug encapsulated at the cost of more leaking out off target, you could get that. Or you can just pick the things that are highlighted in blue, which is what we use in our studies. So we hope that this is a really helpful tool for the field, and it saves some future grad students from the pain that we experienced. So that's useful. So to recap what we've done so far, we found that PFOP nanodroplets resolve the key safety barrier of this approach that other groups have found, which is stability. We found that they also effectively release drug, but only in response to low frequency ultrasound. So we also provide the frequency that you need and the ultrasound parameters that are necessary to get drug release from them. And finally, we've shown a reliable and repeatable method to encapsulate and release various drugs. So the result of this was also a publication in Frontiers in Molecular Biosciences. And more importantly, we have eliminated this critical barrier to clinical translation. So moving on, we next wanted to figure out whether they actually work in non-human primates. So let's get into how we did that. So this is a general overview of the process. We have this monkey setup, which we're demonstrating in the middle here. And we monitored their performance in a visual choice task. So we were trying to modulate the visual system to see if we can actually affect their behavior. So the drug that we chose to use was propofol. And the reason for this was that it's been used in the past. People know that it works in rodents. So this study actually, this is PET imaging. So effectively here, more red means more neural activity, whereas into the yellow and blue, that means that you're suppressing activity. So as you can see from the middle and right plots, they're suppressing activity by delivering ultrasound to that dotted area when they've injected the propofol nanoparticles. So this seemed promising. The nice thing about propofol is that it's a really potent and really fast-acting drug, and it can easily get into the brain. So the effects on behavior we expected to be strong and short-lasting. So we're not going to cause any lasting changes to the monkeys, ideally. So let me just tell you a little bit more about why these large animal models are important, and in particular for ultrasound. So that 300 kilohertz ultrasound focus that we mentioned before affects almost the entire brain of the mouse. If you oriented it a little differently, you could for sure hit a whole mouse brain. And that's completely different to what you're doing in a human with the same 300 kilohertz beam of ultrasound. So it's not really an accurate representation of what's going on purely from a size perspective. A macaque structure and function of the brain itself. So the monkey seems like an ideal way to do this in terms of ultrasound, but also in terms of testing the biocompatibility of the particles. So monkeys' immune systems and things are much more similar to humans as compared to rodents. So to do this, we relied on some awesome work from former postdoc, now professor from our lab, Taylor Webb, who made this amazing system to deliver ultrasound to specific deep brain targets of the monkeys. So we use this array, which is mounted to the monkey's head. And the monkey is completing a visual choice task. So we're doing eye tracking, and we just watch them as they choose various targets on a screen. And we can steer around without moving the transducer at all. So we can target various deep brain areas. And what we're going for is the lateral geniculate nucleus. So what we're showing here, this is MRI thermometry, which is basically you go into an MRI scanner with your ultrasound equipment, you heat up the tissue just a little bit so that you can image it with the MRI, and then you know where and with what intensity you're sonicating. So then we just use the same settings for all of our sessions in the future, and we know what we're doing, at least in a general sense. Another critical part of this was implanting vascular access ports. So these were implanted in the saphenous vein of the monkeys. And this allows us to just have the monkey cooperate and just stick their foot out of the chair. And we can give them an injection. And it's really low stress, and they're not too worried about doing it. And then they can just resume with the task as soon as we're done. And these were implanted and re-implanted and maintained by Caroline. Well, they were implanted originally by Melanie Graham, re-implanted and maintained by Caroline. So shout out to Caroline for being an awesome vet. And so yeah, let's get into the task a little bit so you can see what the monkeys are doing. Okay, so the monkey is looking at a completely black screen originally, and we have them fixate on a target in the middle of the screen. Once they look at that target, we present two targets in succession, and they just have to pick the one that comes up first. So I'm gonna let you do it so you can see if you can get it. So if you picked right, then you would be correct, and you would get a little drop of juice. And then you go on to the next trial. And actually, if you've watched my past presentations, I usually make it easier for you. But this one is an actual monkey difficulty. So if you got it right, you're as good as the monkeys. At least they get this 100% of the time. But you know, we have shorter delays where they're a little bit unsure. And that's a key part of the approach. So what's nice about this is that you get a signed measurement of the neuromodulation. So this is a macaque or a human visual system in schematic form. And as you can see, all of the information from the left and the right side of their visual field is processed contralaterally, which means just on the opposite side of the brain. So our target here is the lateral geniculate nucleus, which is the first relay point for visual information as it enters the brain. So if we deliver our drug here, we can come up with a hypothesis of what's going to happen based on the expected effects. So if we were to inhibit that LGN with the ultrasound or drug delivery, we would expect that the monkeys would be more likely to look left. In other words, they would have a decrease in contralateral choices. On the other hand, if we were to excite activity, we would expect them to be more likely to look contralaterally, and therefore an increase in choices in that direction. So if we just look at the results from one session, this is an example for one of our monkeys. This brown psychometric curve, as they call it, is sort of their baseline. So this is from 5 minutes before we actually apply any intervention to establish what they're doing on that day. So this can change day to day, just based on however the monkey is feeling. So this is a critical thing to control for. So we establish their baseline for the day, and then we deliver our intervention, and then we see where that curve shifts. All right, so this is, again, our major results figure. So I just want to break it down for you so we understand what's going on. So on this plot, there will be a trace that is just their choice behavior over time. And you would expect that if they're looking in the ipsilateral direction more often, then the curve is going to go down. And that would mean that you're inhibiting activity. Whereas if they look contralaterally, it goes up, and then you're exciting activity. So we deliver the injection and the ultrasound. And as you can see, if we inject saline, which effectively is just ultrasound only here, there's effectively no change in their behavior. On the other hand, if we've injected our propofol nanoparticles, as you can see, there's a strong inhibition in ipsilateral preference in choices. And this almost reaches a 2-to-1 preference, which is a huge bias for these monkeys who are doing a task that's really easy. So if you can modulate their behavior that much, it's indicating a pretty big effect happening at the target. And another point that I want to highlight again is that this is 80 sessions in 2 monkeys. So this gives us a pretty good idea that it's safe. And I'll get a little bit more into why and have more data on safety later. But first I want to talk about what exactly 80 sessions of monkey behavior is, because it's really difficult to achieve. So first, the monkey has to trust the researcher enough to go with them out of their home and go do work. So this takes time, and you have to just work with the monkeys a lot, and they won't cooperate most of the time in the beginning, and then by the end, sometimes they cooperate. Aside from that, they have to be motivated enough to work, so they have to be comfortable in their home environment, and you're monitoring their diet all the time. They have to be trained at all the prerequisite tasks. So for instance, Taylor and I spent probably a year trying to figure out how to get our first 2 monkeys, Euler and Gauss, into the chair. It was a great game for them. They got a lot of fruit out of it and it caused us a lot of stress. So they first enter the chair. Then they have to stick their head out of the chair. And then we have to sit still while we put all the ultrasound equipment on them. Then they have to do the task, and they have to do the task without taking naps immediately after we do anything, because then you have no data. Then they have to present their foot for injection, which is actually easier than you would think for some of the monkeys, but other monkeys, it's not as easy as you would think. And then, like I said, they have to keep doing the task immediately afterwards, which is a skill that's trained. And then they have to do it all again the next day. So you can't reward them too much this day because then they won't want to do it the next day. And as you can probably tell, this was a major barrier to getting a lot of this done. So we're really happy that we were able to get a bunch of sessions of data. So anyway, off of that interlude, back to the results. So yeah, this was great. And I actually added in here, we have another condition, which is blank nanoparticles. So this is nanoparticles that have no drug in them. And as you can see, there's no change in the behavior really. It's fairly similar to just ultrasound. To dig in a little bit deeper, this effect is also side specific. So here we're looking at the left LGN versus the right LGN. So when we stimulate the right LGN, you can see they tend to be biased more towards the right. When we stimulate the left, they maybe are biased more towards the left. This gets a little funky when you look at it in this much detail because then you have issues like maybe we targeted one side a little bit more accurately than the other side. But as you can see, they're going in opposite directions. And this is in direct contrast to another one of our studies, which found that ultrasound alone was actually excitatory in terms of behavior. So as you can see, these traces are going in opposite directions. So we're actually overcoming some kind of innate excitation that the ultrasound is likely causing. Okay, so hopefully this is convincing that there was an effect here induced by the propofol in particular. There's way more plots, so feel free to ask questions later. But let's get into safety a little bit. So we have three general approaches to figuring out how safe the nanoparticles are. And first is assessing the pharmacokinetics. So pharmacokinetics, all the drug people are already aware, but this is effectively how long the drugs are available in the bloodstream is that first plot. And then the second plot is where those drugs wind up after they're cleared from the blood. And as you can see, they have a half-life in the bloodstream past research. So this is a fairly good sign that we're doing something similar. And they're generally accumulating in the liver, which is where most general particles of this size accumulate. Next, we moved on to doing repeated blood tests for the monkeys. So this is effectively like what you would get if you went to a doctor and you were worried about your liver or kidney health or what have you. We did a whole panel of blood tests to assess whether or not they're having any reaction to the particles. And any effects that we saw were transient. They went away by the end of the study. And most of them were well within normal ranges for the monkeys. So then we moved on to assessing whether or not the tissue itself in the brain was affected. And this was a series of MRI images. So maybe ideally you do histology, but since we had monkeys and we wanted to keep working, the best we get is MRI. And on the left here, this is a metric of blood-brain barrier disruption. So any highlighting in yellow would indicate that the blood-brain barrier has been disrupted, which as you can see, there was none at focus. The little spots of yellow around are likely from blood vessels where there's a contrast agent, so it's probably just hanging around still. And then on the right, this is an MRI imaging protocol, which would allow you to detect edema or any lesions in the brain. And we didn't see anything of that kind at the target either. Now, I actually want to highlight another blood test study that we did. And this was work that Audrey helped us with. And this was a 6-week repeated dosing period. So in this, we actually ramped up the dose from a very low dose to a dose that's higher than what we used in the behavior studies. And then we repeated that. So this was over a total of 6 weeks. And as you can see, any effects in terms of blood, either 1 or 7 days after administering the particles were fairly minor. And I just have labeled this with liver, kidneys, and immune response. This is generally what we're looking for with each of these. And again, there we have a whole bunch more blood data. So if you want to see that in question time, feel free to ask about it. Okay, so let's recap the outcomes of this part of the study. So first, we found that propofol released from the PFOB nanodroplets can locally suppress neural activity in primates. It's our main finding, and that they pose minimal risk to these non-human primates. So we've used them repeatedly and not found any signs of damage or, response to the particles themselves. So aside from that, there was a bunch of scientific output from all this monkey research. In particular, this paper that's mostly describing what I've talked about in the Journal of Controlled Release this year. So that's cool. And critically, we've eliminated another barrier to clinical translation that we've demonstrated that they're both effective and safe in non-human primates. So then we move on to our last problem, which is the human skull. And I had to bring in some help on this one because, this is getting a little bit out of my wheelhouse. But so this is just demonstrating the problem here that we have, which is getting effective drug release in the skull. As you can see, these skulls, this is 3 different people in a CT scan. As you can see, the skulls are really irregular within each one, and they're completely different from person to person. So it's really difficult for people in the ultrasound field to figure out how much ultrasound you're getting through, which makes it difficult to actually do the dosing of the drug at the target. And in fact, some research that Tom has done in our lab found that ultrasound is attenuated by somewhere between a factor of 4.5 and 64. So this is a huge range, which basically means that if you don't correct for the skull in some way, you really have no idea what kind of ultrasound you're putting into the brain. And the sort of hypothetical question is, how does this affect drug release? And to test that, we used this ex vivo skull setup. So on the left, this is kind of that's a rendering of it. So we have a skull that's cut in half, and we put our test tube similar to in the first section. We just put it at the focus of the ultrasound, and then see if we can get drug release in the same way as before. And initially what we found is that, as predicted, the human skull severely attenuates drug release. So this is an ideal correction, which is effectively the same as if you were just doing it in water with no skull there. You get a whole bunch of drug release. With no correction, you get basically none. And in fact, it's pretty much the same as if you didn't turn the device on at all. Fortunately, Tom has come up with this awesome device to deliver a predictable dose of ultrasound into the skull without any extra imaging. So this is really practical, and they're already using it for a bunch of studies, which they could tell you about. But the general principle here is you have an array on each side of the person's skull, and you emit a little pulse of ultrasound from each element on one side and record it on the other side. So then you can just compare what that's like in water versus what it's like with a human head there. And then you can correct the beams in terms of their timing as well as their intensity with that. And Tom showed in the past that you can effectively restore the amount of ultrasound that you want at the target by doing this. But the question still remained whether or not we could do this with drugs, if we could effectively release drugs at the target. And what we found is that similarly, we're able to restore effective drug release as if there was no skull there. Really importantly, this is it works over various ultrasound pressures. So ultimately, using the pressure to determine the dosing that you do at the target is probably going to be a strategy that's used. So as you can see, if we increase the ultrasound intensity, we're able to get more drug release, and that's maintained using this correction method. As a little bit more evidence of the focused nature of the approach, this is a sham condition where we steered 10 millimeters away from the vial. So the ultrasound is now focused somewhere else, and you get effectively no drug release again. All right, so this work resulted in a co-first author publication between Tom and myself. And just while we're on it, recap, this was all of the publications that came out of this. But more importantly to me, again, is that we've removed a whole bunch of barriers to clinical translation to get this closer to actually being used in humans. So let's just run through a little recap of everything we've talked about. We developed stable ultrasound responsive drug carriers, as well as provided the parameters that you need to activate them. We validated that it works in non-human primates and that it's safe so far. And we've shown effective correction for the human skull and restored drug release as though there were no skull in the first place. So we've done a whole bunch, but there's still a lot more to do for this to become useful. And the first area that I think is really exciting that the lab is going down now with Josh and Audrey, they've already figured out how to encapsulate 2 more drugs and particles, afatinib and doxorubicin, which they intend to use to treat glioblastoma in mice and hopefully someday humans. This is sort of like a campaign that I really think it would be cool to do. Hopefully someone in the lab will do it eventually. So you might have heard about ketamine or psychedelic treatments for depression or other mental disorders. So these drugs seem to be really potent for treating depression in particular. But a major barrier that's held them back is that you go through this whole psychedelic or dissociative episode, which makes them more risky in terms of side effects, as well as it takes a lot of monitoring to actually go through them. So I think it would be really interesting to figure out if we can actually rewire these neural circuits by delivering these drugs to specific targets, and then avoid the dissociative effects, but still get the neuroplasticity. And I think this would be really cool to study in monkeys, and it's an awesome opportunity. It would be great scientifically to see if that's even possible. And plenty of people think that the psychedelic effects are needed to get the plasticity, and we can figure that out here. And finally, some sort of feedback mechanism to do accurate dosing, I think is going to be important. One idea is potentially to use ultrasound imaging to look at sort of the intensity increase after you stimulate the particles, and maybe you can correlate that with drug release. So this is an ongoing area as well. And I think all of these are promising techniques to eventually get us towards this dream, which is delivering drugs specifically where they're needed and not elsewhere. Jan for mentoring me all this time, and Taylor, who went through all this monkey stuff with me, which was constant chaos, and as well as everyone else in the lab who helped out. Tom always was giving me good ideas. The A team, as I call them, that chipped in on nanoparticles were amazing. And also, I thank Caroline for being an awesome vet again, because I don't even know what this presentation would have been if you didn't come here. Yeah, and also, of course, like, big thanks to all of my family and friends. Thank you all for coming. Allison for giving me the kick in the butt to finally finish. And my parents for not letting me quit at a whole bunch of different times throughout. So yeah, I'm happy to take questions. Like I said, I have more slides. If you ask the right questions, you can get access to those. And we have this fun tossable microphone. So we can just, we can have a whole discussion here and it'll be pretty fun. So yeah, thanks. And anyone in Zoom, feel free to either unmute yourself or chat.
So one of these articles actually is in press now. So there is a press article coming out of Matt's work. So you can kind of see how much impact it will have. But feel free to ask questions.
Yeah. You get to hold the cube if you ask a question. Oh, you're good.
You disorders. What kind of practical limits are there on the drugs that you can actually load into these nanoparticles? And what do you think would be an example of a drug that you haven't tried yet that you're really interested in besides the psychedelics?
Yeah. So far, the drug has to be hydrophobic to get in, and also probably a small enough molecule. Although Josh might have gotten around that issue, but generally it's that it needs to be hydrophobic, which is nice for the brain actually, because small hydrophobic drugs are the ones that are likely to get into the brain and get across the blood-brain barrier. So yeah, I'm really interested in ketamine. I think doing the immune suppression study would be really interesting. Of course, I would need a collaboration with someone else. But yeah, I think that would be cool. Obviously cancer, that's really the big one as well. Like it's, you need a localized treatment in a lot of cases, and that would be a great area for that. A lot of those are hydrophobic too, so it's useful. But aside from that, it might not be like a permanent barrier that it has to be hydrophobic. Some people have experimented with using actually a double layered approach, so that then actually the inside of the particle is hydrophilic stuff again. So you could maybe incorporate different drugs that way. Good question.
Great talk. Wonderful work. What do you think is the, this is weird talking to you.
Yeah.
What do you think are the major factors that determine termination of action after you step? And are there ways to?
Yeah. I think that's likely something. So it's mostly, I think, in terms of the drug itself. So in the case of propofol, we saw a really fast turn off basically of the effect. So they went back to baseline really quickly. So, using different drugs, I think likely you would get different amounts of time there. We have done a little bit of work on figuring out whether there's any effect of the particles themselves still releasing drug after the ultrasound is off. And what we found so far is that it seems like they're not releasing drug after the ultrasound turns off. So basically, it's only while it's on that they're more permeable. And I think that's potentially unique to these higher boiling point cores. So other people have studied some much lower ones that they've actually condensed. They're a gas at room temperature. They've condensed them, and then they expand, and then they're permanently a bubble after they've expanded. So I think in that case, you likely would keep getting release as they float around. But yeah, I think in our case, it's likely mostly the drug itself that determines it.
So does that mean if you wanted a persistent effect, you have to repeatedly pulse?
Yeah, I think you could repeatedly pulse. And as well, so they're cleared pretty quickly. So you could probably just do an infusion of the nanoparticles and continually pulse with ultrasound, which I think is that's what you guys have done clinically. You do like a long time pulsing, right? So it's feasible to continually pulse the ultrasound. So yeah.
Looks like Nico has.
Oh yeah. Go ahead, Nico.
All right, thanks. Good talk. So I'm not exactly sure how long you had these monkeys testing for, but obviously at least a couple months for 80 sessions. I'm wondering about the long-term safety of PFOB, given that it's, a halogenated chlorofluorocarbon, which CFCs were banned in the 80s. And now there's this emphasis on PFAs and their long-term safety and health effects. So is there an alternative to a fluorocarbon for the working gas of your nanoparticle? Or do you know the long-term effects of your nanoparticles?
Yeah, so obviously we don't know the long-term effects beyond the 6 weeks that we've specifically monitored in our case. But like I mentioned, the PFOB in particular was studied at much higher quantities in humans for a while. And I think they found the PFOB itself is cleared within a few days from the body. So you wouldn't expect like huge effects. I guess it could be different if it's in the particles. So yeah, as far as an alternative to get to that part of the question, I'm not aware myself of any alternatives. So these perfluorocarbons are also used in microbubbles in clinics. Yeah, they're used in a bunch of different things. I know the new PFA stuff is kind of interesting for that and probably not ideal, but yeah, I'm not sure 100% if there's an alternative.
Thanks.
Mhm. Cool. All right.
Additional questions for Matt? Ask any question that you would like. I'll pass to move forward. Casey.
I think there are some small drug reads there's around 40. How can we measure their some kind of reads of drugs or drug release?
Yeah. Yeah, that's a good point. So there is likely some release. Well, actually, we kind of know that there's some release away from the target. So we actually tested much higher concentrations before we settled in on what we use now. And we were able to see the monkeys kind of like the effects of the propofol happening. They looked a little sleepy. So yeah, there is some off-target drug release happening. I think it's a fairly minimal amount. Other people have done imaging studies that have shown that it's fairly localized in terms of the concentration of the drug directly. So it seems like at high concentration, it is localized. Another thing that ties a monkey, it's just because it would diffuse so much throughout the body. It's at a really low concentration everywhere else generally. But yeah, you could definitely do some, if you wanted to study that in more detail, you can maybe do some fMRI studies with propofol, see if there's activity decreasing or EEG or something that would be fairly easy to implement as well.
So if I use the same molecular weight of the knife with same molecular weight is propofol, or do you think it should be some proof of the?
Oh yeah. So if you used a marker that is similar to propofol, yeah, I think that would be a good approach to doing it. Yeah. Oh, there's a chat.
Well, I wanted to ask about the shell. Is there a reason that you chose the polymer you chose, and why you went for the polymer instead of like a lipid carrier or any other carrier system?
Yeah. Well, I'll start with polymer versus lipid, and the main reason actually is just to replicate past studies. So we went with polymer because that's what people have studied in the past, and they've chosen it for stability reasons primarily. So it lasts longer in the bloodstream. Like I mentioned, those liposomes tend to break down pretty quickly. Yeah, and so the polymer actually itself has a PEG polyethylene glycol outer layer, and that's used in all kinds of drug delivery and medical applications. So it's been studied really thoroughly. And then the inner part is PLA, which is another polymer that's used a lot. So basically we did it for biocompatibility reasons. As far as like the chain lengths in particular, we played around with a few of them. And we wound up landing on the one that seemed to work the best in terms of encapsulating and releasing the drug. I think it would be interesting to play around more in future applications, maybe increasing the length of the outer chain if you wanted to make them more stable. I think there's reason to believe that that could work. Or, increasing the length of the the hydrophobic chain, maybe to encapsulate more drug. So yeah, there's definitely areas that you could change them for your applications. Yeah. Great.
So you have now validated the effectiveness and safety in a non-human primate. So that's a major milestone. Congratulations.
Thanks.
It's easy to do this. Having achieved that milestone, it appears to me that it's not very far from advancing that into humans. And for instance, for better or worse, big pharma may be interested in this, right? Because many of the drugs that they have developed actually cannot make it into humans because it interacts with the heart. Heart is the main barrier for many drugs and potentially some other organs. So actually, many of the drugs have to go off the shelf. And you're protecting the body from the direct interactions of the drug with those organs through those shells. May actually bring many of these developed drugs and medications back and make them relevant again. So I could actually imagine a big interest for better or worse from big pharma. What do you think are the steps necessary to get there? Maybe once you join industry, you may be one of the liaisons. What do you have to do?
Yeah, that's a great question. So I think specifically in terms of the enabling the use of more drugs, I think there might be a need to do more studies to figure out actually how much is happening off target. So if you have a drug that's toxic to the heart, we haven't specifically quantified, what's going on in the heart. So I think it would be important to know how much is leaking there and what effect that has before those more risky drugs are used. And even chemotherapeutics, I think that's probably something to think about as well, since most of the particles wind up in the liver. Doxorubicin is likely toxic to the liver, aside from being toxic elsewhere too. So I think figuring that out is going to be an important thing to do. Yeah, in addition, I think picking the right application is probably an important thing to do there. So like you mentioned at the beginning, glioblastoma is really deadly. So they're willing to try some things. But kind of have to be careful with that too. If things go poorly in that, then that's not a great first step. And then you don't want to run into a roadblock right at the beginning. Whereas maybe more mental applications, you don't have that as much. So, yeah.
Concerning the polymeric shell and translation to other drugs, do you think it would be an issue if you had a drug that was a lot stronger and more toxic than propofol, that it would actually degrade the polymeric shell and you would need a stronger coating for that? So it wouldn't just leak to the rest of the body due to the toxicity of the drug alone.
Yeah, that's a great point. I think, yeah, it probably is definitely worth studying the drug and nanoparticle interaction before using it, in terms of probably stability at that point and over time. Yeah.
One more thought, what about pain? Chronic pain, and let's say release of ketamine in mechanical pain that works. It seems like potential target.
Yeah, I think that that would be really interesting to do. Yeah, I'm not sure, I guess in chronic pain specifically what ketamine in particular does. You'd have to look into what kind of receptors are in those areas as to what's going to happen when you deliver ketamine there. But yeah, that seems like it could be a good application. And as well, you could, so I guess something that I didn't really mention in the main presentation is the overall structure of a treatment, that you could potentially be using different drugs throughout it. So maybe you could identify what area is problematic for a patient using propofol since it acts really quickly and then is gone pretty quickly. You could use propofol to figure out what areas you need the drug and then deliver a more potent or longer lasting drug there. So yeah, that could be a good approach to doing that.
And how about releasing a drug in, let's say, dorsal ganglia, so you directly block the signals coming from the periphery and it doesn't even reach the brain? Do you think that approach would be feasible?
That's an interesting question. I don't know what the blood supply in the spinal cord is like. That would be something to think about.
The giardia are very.
Oh, right, dorsal root ganglia. Yeah.
They're
Yeah,
very
yeah.
highly vascular.
Yeah. So I think that would be a good approach, and they're easy to target with ultrasound, like you guys are working on. Yeah, I think that could be interesting as well.
All right, last one, in terms of clinical applications, these nanoparticles needed to be made and injected on the same day. So if we were working with the patient, would the person administering the nanoparticles need to create these like a few hours in advance before administering it to a patient?
Yeah, so for animals, the protocol that we've been using, yeah, you want to make them immediately before, which is probably a limitation long term, or maybe not a limitation, but it's something that still needs to be improved before they could be used in humans, in my opinion. So other groups have actually looked into adding in various additives, and then you can freeze them. So then their shelf life is increased that way. So that would be something to try. Again, you want to validate that method as well, that it doesn't change how they function. But yeah, so yeah, and then the manufacturing actually is for it definitely needs to be scaled up for humans in some type of way. So that's going to be another interesting thing to figure out.
Question. So that was a very big talk.